So key exchange is an issue in public key cryptography. Uh, Sorry, private key cryptography. So people have been studying other methods for cryptography, and public key cryptography is an alternative. And in public key cryptography, each party, the communicating parties, they have different encryption keys, and these are publicly announced. So everybody knows how to encrypt for everybody. Okay, so this means everyone knows how to encrypt for a specific target. But this doesn't mean they can easily decrypt an encrypted message. So as opposed to private key cryptography, in public key cryptography, knowing how to encrypt the data does not necessarily mean you know how to decrypt. That is the key issue here. And for that reason, you can announce your public key, but obviously you hold back some key components of your encryption procedure so that it's not automatically easy to find the decryption method. Now, this idea dates back to the work of Diffie and Hellman. These are quite famous in cryptography. The first principles were laid out by them, but the first practical public key algorithm was laid out by Rivest, Shamir, and Adelman in 1978. And due to their names, we call this algorithm the RSA algorithm. And this is still one of the most widely used algorithms in cryptography. And of course, there are other methods, for instance, algorithm encryption or some elliptic curve techniques. If you are interested, you can look these up. It's quite a deep subject, but we are going to focus on RSA in the context of this course. But do not forget that is not the only way. I'm just showing this as an example of how the theoretical stuff we studied in modular arithmetic and prime numbers translates into a real-life application. So first of all, we are going to see how encryption is performed in RSA. The encryption key in RSA is in the form of NE, a pair of numbers, where N is the product of two prime numbers, P and Q, and E is co-prime to the number P minus 1 times Q minus 1. And why is this is going to be more clear when we talk about decryption. Now, typically, obviously, RSA encryption is performed in binary because that's what computers work in. But here, to understand how it works better, we are going to study it on simple decimal numbers because it's going to be more difficult to follow the procedure when this is performed in binary. So what we are going to do is just as in the Caesar cipher, we are going to map numbers, decimal numbers, to each letter, A, B, C, up to Z. So the numbers 0, 1, 2, etc., up to 25 are going to map to A, B, C, etc., up to Z. What we are going to do is, since potentially we can have two-digit numbers, we are also going to pad the one-digit ones with a 0. So A will be 0, 0, B will be 0, 1, C will be 0, 2, etc. And the message M, the original data, is obtained by partitioning the data word into equal and appropriate size blocks. This is going to be clear in a moment. And when you have this, each block, and this here is represented by the message M, is encrypted via this. C, the code word, equals M, the message, to the power E. E is given here in a part of the encryption key, modulo N, and N is this number here. So M to power E modulo N. As we have seen, there are a number of efficient ways to compute exponentiation. So this is the encryption itself is not a difficult problem. Let's see an example. Suppose that the numbers n and e are 2537 and 13 respectively. Here, this corresponds to the number n, corresponds to the product of 43 and 59. Okay, observe that these two numbers are prime numbers, p and q are prime, and their product is part of the public key. And we are going to encrypt the message stop. So first of all, we need to obviously encode this in our representation. A is 0, 0, B is 0, 1, etc. And in this scenario, S corresponds to 18, T corresponds to 19, O is 14, and P is 15. So you concatenate them together, your data stream becomes 18, 19, 14, 15. So an 8-digit decimal number. Okay, so we are going to split this into blocks, and the choice of the size of the block depends on n here, because n here is 2537. That determines your block size, because you don't want a block exceeding n. So you would like to work in set of z sub n. So you want every block, every message be in this set in order to avoid ambiguity. Therefore, you need to select 2 letters at a time. Because if you select 3 letters at a time, for instance, the message ZZZ is going to be this number, which is going to be larger than n. Therefore, you are going to lose the distinction between certain code words, and you do not want that. So you do not want your blocks to exceed this number. Hence, you need to use at most 2 letters at a time. So at most you will get is 25, 25 in that case, and that is less than 25, 37. So that means we group 2 letters at a time to obtain the block or the message n. In block 1, we have the number, well, this was the original data stream. So you partition it into 2, 18, 19 first, and then 14, 15 next. So 18, 19, you raise it to power e, and e is 13 in this scenario, and then take modulo n, 18, 19 to power 13, modulo 25, 37. These are just decimal numbers. Okay, 18, 19 is what? 1819 to the power 13, modulo 25, 37. This is 2081. So that is your first code word. And well, this should be block number 2. And that is 1415. You raise it to power e, which is 13, and take modulo n, and 2182 is the result. Therefore, the encoded result is 2081, 2182.